Okay, so I was saying, when we're talking about Hooke's law, we're going to be dealing with the spring. So we said, let's say this is the spring, okay, and then you are trying to stretch the spring. So there is this original position which we call equilibrium position, okay. So this position, the displacement which is x is always zero. Now, when you are trying to stretch the spring, you are going to apply the force. That applied force is going to be in that direction. Now, this spring will try by all means to go back to its original position. Now, the force that is pushing the spring to go back to its original position is what we call the restorant force. Okay? So, since the restorant force is moving toward negative x-axis, then we are going to say that the restorant force is given by negative kx, where x in this case is the displacement. Okay? It's the distance. So if I try to stretch the spring from this point all the way to that point, this x is what I'm going to call, this x here is my displacement. So k is constant, you're going to be given. Okay? It's what we call the spring constant. So k is the spring constant, then x is the displacement. So now at equilibrium, x is always zero. So when they ask you to find the restorant force at equilibrium, the restorant force is going to be zero. Now let's assume to say you are compressing the spring. Okay, here is our spring, then this is the original position, so you are compressing it. So my original position now is there. At this point, x is zero. Okay, so we are saying that from this point all the way to that point, that's where I'm going to have x. Now since I'm compressing the spring, x is going to be negative. Okay, because this displacement now is moving toward negative x-axis. So if I'm stretching the spring, x is positive. If I'm compressing the spring, x is negative. Now what about the restorant force? Since you are compressing it, meaning that the applied force now is in that direction, the applied force is the one which is going to be negative. The restorant force, you are trying to, the spring is trying to go back to its original position, meaning that the restorant force is now what? Positive. But still, the formula remains the same. So the restorant force will still be negative kx. So even if you are, when you are stretching or compressing the spring, the restorant force is going to have negative still. Okay? Because of the same principle. Any question there? Do you have questions? Okay. Okay, we continue now. So now since we are saying that if I have the spring, I'm trying to compress it. The general principle which I want you to get here is that the applied force is positive, the restorant force is negative. So the formula remains the same, negative kx. So this is my equilibrium, meaning that from this point here, from this point all the way to that point, that is going to be my plus x. If I'm compressing it, let's say I've compressed this spring to this point, meaning that from this point all the way to that point I'll have negative x. Okay, but the formula remains the same. So what is the value for k? Okay, I'm asking, what's the value for k? what's the value for K? We are saying that the resultant force is given by negative kx. So what is the value for K? It's a spring constant. So what is the value? Mm-hmm. It's a constant. So now if it's a constant, okay, I can give an example of G is constant, not so, which is 9.8 meters per second squared. So K is also constant. Now what is the value for K? Yes, please. Yes, it's a negative number. Hmm? Yes, the value. Mm-hmm. Yeah, the same one. I want the same one. Okay. Okay, you find out. Okay. So now I think we can continue. Now I want us to focus more on this formula. We are saying that restorant force is given by negative kx. Okay. But we also know that force is given by mass times acceleration. So we can be able to find the maximum acceleration if I replace this with F here. So I can say my MA is going to be negative kx. Is that okay? I'm talking about the restorant force. The restorant force is the force which we all know to say is the mass times acceleration. So I'm just replacing where there's F with MA. Is that okay? Is that okay? Okay. So now I can also use another formula. I can divide both sides by m, even here by m. Then these two will cancel. I'll have a to be equal to negative k x over m. But now, if you are trying to compress, we are trying to find the formula which is going to help us to find the maximum acceleration. So if you are trying to stretch the spring, if you have reached at the maximum position, meaning that this distance is what we are going to call the amplitude. So you only call it the amplitude if you have reached at the maximum position. That's the reason why I'm saying that we are trying to find the formula which is going to help us to find the maximum acceleration. So the maximum acceleration, meaning x in this case, is the same as a, but only that a shows us to say we have reached at the maximum position, meaning that for us to find the maximum acceleration, we are going to say negative k over m times a. Perhaps you have seen this formula. So this is where it's coming from. This formula is very, very important. We need to know it. Is that okay? Is that okay? Okay, so I've got one example here which we're going to solve. I'll not be able to type it, but I'll just read it. The question is A 0.35 kg object is attached to a spring. So I'm going to give you a free body diagram. A 0.35 kg object is attached to a spring of a force constant or over 1.3 times 10 to the power 2 Newton meter. Can you mute your mic? Mute your mic. Okay, thank you. So the question is, we have got an object which is attached to the spring. So this object, they are saying that it has got the k, which is the constant. So this k, they can change, but they'll give you always times 10 to the power 2, but it is always in Newton meter. You can use dimension analysis to see if it is indeed in Newton per meter. Because this x is in Newton, it's Newton per meter. X is in meters, force is in Newton. So if you divide both sides by F, you discover that you have this. So this is Newton, this is meter. That's why it's Newton per meter. Okay? Now that is the spring constant. Then we have been told that the mass of this object is 0.35 kgs. So the question is, a 0.5 kg object is attached to a spring of a force constant of 1.3 times 10 to the power 2 Newton meter, is free to move in a frictionless horizontal surface if the object is released from rest at x is equal to, if it is released from rest at x is equal to 0.1 meters. Find the resultant force and the maximum acceleration. Okay, so how do we find the resultant force? So the resultant force is given by negative kx, and we know that this force k, we have been told that is 1.3 times 10 to the power 2. The x, we have been told that is 0.1. Okay, so meaning that the force, if you're having a calculator, you can help me to find the answer. So what is 1.0 or 1.3 times 10 to the power 2 times 0.1? So I'm getting 13. I'm getting 13 newtons, which is negative 13 newtons. Can you confirm? Okay. Then another question is, find the maximum acceleration if the amplitude is 0.5. So to find the maximum acceleration using the formula which we just derived, so the maximum acceleration is given by negative k over m times a. Now we have everything, so I'll have negative 1.3 over the mass, which is 0.35, times the amplitude, which is 0.5, meaning that I'll have 1.3 divided by 0.35 times 0.5. What are you getting? I'm getting 1.8, not 1.5. 1.3 times 0.5 divided by 0.35. I'm getting 1.85. Yes, please. 1.857. So acceleration is always in meters per second squared. Thank you. Okay, then I found this question from another past paper, which they just brought a diagram. They said there were two spring. The first spring, I think this was in test one, I think for 2015, somewhere there. Okay, then another one, it was like this. So you see here. So they are saying that after putting this block of mass 0.55 kgs, then they discovered that the spring was stretched from this point all the way to that point, and the distance they gave was 2 centimeters. Okay, the question was, the first question was, find the force, find the restorant force. That was the first question. Then the second question was, find the spring constant. The first one was, find the restorant force. Then B was, find the spring constant. The spring constant. Okay, now this is different now, since we know that for us to find the force, this is the applied force which was going in this direction. Okay, then there is a force which is moving in this direction. That is our restorant force we are looking for. But this force and that force is the same, only that for this force we need just to put the negative. Okay, for this force, the restorant force. So the restorant force in this case is going to be the weight of this block. Therefore, I'll say the force is going to be mg, because the weight of this block is the one which made this block to be going down. At the same time, the normal force is the one which was pushing it to go back to its original position. Okay, so I'm going to say the restorant force is going to be, the mass is 0.55, g is always 9.8. So once I find this force, this is going to be my restorant force. So it's going to be 0.55 times 9.8. So I'll be able to get 5.39. Now this is in Newton. But remember, this force has to be negative, but I'm going to include negative when I want to find the spring constant, because the spring constant has to be positive. Okay, so a constant will always be positive. So to find the spring constant, we'll use the same formula. We'll have x negative kx, but I know that this restorant force, when it was going up, it had negative, meaning that when I plug in this guy, I need to include negative, so that that negative and this negative should be cancelled. The x in this case is the distance. Is that okay? So the x in that case is the distance. So I'm going to say, I can just get rid of this. I'll say F will be equal to negative kx. So I have this, I'm going to put negative, so that that negative and that negative should be cancelled, because k will always be positive. So I'll put negative k. The x is the distance, which is 2 centimeters. Now in this case, this is centimeters. I have to convert this from centimeters to meters. So I'll say 2 divided by 100, which is going to give me 0.02. So I'll divide both sides by negative 0.02. even here by negative 0.02. So this can go. So my K will be equal to 5.39 divided by 0.02. So I'm getting 269.5 Newton per meter. Any questions so far? Do you have any question? The first question was asking us to find the resultant force. Sorry? How did we end up finding what? No, we have answered the first question. The first question, the answer was 5.39 newtons because we used the weight of the mass, the weight of the block, which was 0.55 kgs. Now, in this case, we didn't use this formula because we were not being given the K. Again, the second question was asking us to find the K. When an object is in free fall, yes. Okay, so now here I have given you two scenarios. In a case where you have been given this spring, which is just horizontally, you can't think of resultant force to be equal to mg. Okay, but in a case where the spring is placed vertically, yes, it's going to be equal to the mg, because the weight of this mass or the weight of this block is the one which is going to be the applied force in this case. You know that, right? The weight of this block is the one which is going to be making this spring to be stretched. But in a case where the spring is just horizontally, you have to apply the force yourself for this spring to be stretched. But in this case, as long as you put this block, this spring is going to be stretched, meaning that the force that has made that the spring to be stretched is the weight of that block. Exactly, yes. The applied force is equal to the resultant force. But in this case, we are only interested in the resultant force because it's the force that makes the spring to go back to its original position. So we are interested in the resultant force, not the applied force, but they're the same. Because once we consider the applied force, meaning that this formula is going to be positive, but the formula is always negative because we are talking about the resultant force. If you go back to Newton's third law, for every action there is equal but in opposite direction. You have the same value, but another one is going to be negative, another one is going to be positive. Yes. Mhm. No, they can't ask you to find the applied force. It's not possible. But if they ask you to find the applied force in this case, then you just say it's the same as the resultant force, but it has to be positive. In a case you don't consider the force. Okay, what is happening here is the resultant force is always in opposite direction with the applied force. Okay, that is the same. If we go back to Newton's laws of motion, I can give you an example of if you have this. If this is the surface, then you have got an object. If you are pushing this object in this direction, meaning that the friction force has to be applied in that direction also. But friction force is always negative, not so? Yes, friction force is always negative. So it's the same. Even if you have got an object moving in this direction, then the friction force is applied in that direction. Still, the friction force is going to be negative. So it's the same. It's the same principle. Exactly. No, they'll always give you, if they give you the spring constant, in this case, only that I'm going to give you the full question, but the question was saying it was moving under the influence of gravity. That's the reason why I've used G. But there's another question, I think I saw it. It was, I think it came in 2016, somewhere there. They gave the spring constant and then they asked to say find the displacement. So in that case, you use the spring constant. So in this case, I've used the G because I've not been given the spring constant. Sure. Is that okay? Uh-huh. So in a case where you have been given the spring constant, you use the spring constant. Now in this case, I've used this formula because another question was asking me to find the spring constant. But each question they are going to give you spring constant. Yes, that's how it is. Is that okay? Do you have the throw sheet for second semester? I want you to send them in the group. There is a question which I want to show you. Okay? There is a question which I want to show you. So now we can go back to our spring. I want to explain something else. So here is our spring. Now I've told you to say at equilibrium position x is always 0. So as long as you see a question which is asking you to find uh, the resultant force at equilibrium position is always 0 because x is 0. So 0 times anything is going to be 0. Okay? Now I want to introduce a very simple concept which is elastic and potential energy. Okay, I'm going just to introduce it and then we are going to finish tomorrow. So if you have got the spring, this spring is moving. Okay, if this spring is moving, we expect to have the potential energy. So there is what we call the elastic potential energy. There is gravitational potential energy and elastic potential energy. Elastic potential energy is the energy stored by the spring, and this energy is always given by half kx squared. Then gravitational potential energy is the one we call mgh. Why are we saying mgh? Because it is under the influence of gravity. At the same time, we're going to have h. Okay, if I may take you back to work, energy and power. If an object is on top of the building, here is an object, this building is going to have h. So if this object is falling from the top, meaning that it is under the influence of gravity, that's why we're calling it gravitational potential energy. Now this one, it is the energy stored by the spring. That's why we're calling it elastic potential energy. So in tutorial, I think it's tutorial sheet 1, there is a question which they asked you to show that the work done by the spring is given by, you can mute your mic. Can you kindly mute your mic? Okay. So there is this question. I'm going to explain more about this energy. I'll also explain about mechanical energy and kinetic energy tomorrow. But for now, I just want to explain about potential energy. So we are saying that the potential energy is the energy stored by the spring. Elastic potential energy. That's why there's BES. Elastic potential energy. Then this is gravitational potential energy. So if they ask you to find the gravitational potential energy, you use this formula. They ask you to find the elastic potential energy, you use this formula. Okay. Now, in this case, what I want you to understand here is the elastic potential energy is the same as the work done by the spring. Okay. Now there is a question which they ask to say show that the work done by the spring is given by half kx squared. So I want to show you where this formula is coming from. Okay. So I'll start from here. We know that work is equal to force times distance. If I may take you back to semester 1, work done by the object, by any object, is given by the force times the distance. But in this case, we have said that when we're dealing with the spring, the distance is the same as the x. So I'll say that the force is given by, the work done by the spring is given by the force times x. Okay. So now we also know that the force which we are talking about here is the resultant force. So I want us to ignore the negative for now because it has no effect. The resultant force, we have said that is negative kx, but I'll just say is kx, meaning that I'm going to replace where there is F with kx. So work will be equal to kx, or before I go there, I want to introduce the issue of the concept of calculus. I'm going to differentiate, or not differentiating, let me say I want to integrate. Why I'm trying to integrate? Because I have got x here, meaning that for me to have x squared, if I integrate x, I'll have x squared. Not so. Integration. So if I integrate this side, I'm going to have this. So meaning that I'm going to integrate this with respect to x. Meaning that this x is going to disappear, then it's going to be replaced by dx. Okay. So now what I'm going to do here is I'm going to replace F with kx, because the resultant force is given by kx. So I'll say the work done will be equal to the integral, where there is F, I'm going to put kx. Then I have the x. So I'm integrating this with respect to x, but k is constant. What do we do? If I want to integrate this, if maybe I have the integral of 2x, what would be the answer? For those who remember integration, okay, the integral of 2, what would be the answer? So this one from grade 12, we are saying this one is going to be dx, then it's going to be 2x plus c, if you remember. So the x, the power increased by 1, you divide by the power. That's what we do. So here, meaning that the work done will be equal to k, then I'm going to have x, Then this x, we say 1 plus this is to the power 1 plus 1 divided by 1 plus 1, which is 2, meaning that I'll have k x squared over 2. So the work done will be equal to half. This is the same as half kx squared. So this is where this formula is coming from. So at the same time, this is the formula for elastic potential energy. Is that okay? Or you are lost? There is a question from throw sheet. Show that the work done by the spring is given by half kx squared. So this is how you show it. Is it okay? Come again. I think it's tutorial sheet 2. Tutorial sheet, no. Tutorial sheet 1 for semester 2. Tutorial sheet 1 question, I think it's question 1 or question 2. Do you have question? Okay, so we need to go to conservation of energy, but that will be maybe tomorrow. So for today we end there. If you have got any question, you can ask. So for free classes for physics, I think this is now for free. Next time we're going to have physics, we are going to have only registered students. So if for those who are interested, you can register with us. It's only 8 kwacha per course per month. You'll be able to access our private videos from website. Then you'll be able to access the online classes. So if you want to make payments, you can inbox me. You have my number. Or if maybe you don't have my number, here is my number. 0767 72 9927. So get in touch with me using this number, and then you'll be able to access our videos from website. At the same time, you'll be able to access the online classes. Thank you.